All right, we are going to look today about some correlation coefficients, and we're going to look a little bit about how correlation is different than causation. So we will explore those two topics today. Um, the nice thing is that when data follows a linear pattern, we can do much more with it. And one of them is look at correlation coefficients, and we can eventually get to use it to make predictions and do all kinds of things. So, and there's many, many things in life that follow a linear pattern, and we'll see some examples as we work through the rest of this chapter. But linear patterns are fabulous, and the first thing we're going to talk about with them is correlation coefficients. Okay, so correlation coefficient basically is a number that describes the direction and strength of a linear relationship, and it has to be linear between any two variables. So they have to be related. It does not have to be a cause and effect relationship between two variables to look at correlation coefficients. They just have to have some sort of a relationship. Okay. If your R value is positive, then you will have positive association, meaning if you graph it, it looks like it has positive slope. Obviously, if your R value is negative, you'll have negative association, meaning when you graph it, it has negative slope. If your R value is 0, that means there is no association. And I probably should throw the word linear in there, no linear association, because if you have dots that are like in a perfect parabola, it may look like it is a really strong association, but it's not a linear association. And so when you calculate correlation coefficients for that, your R value will be 0. Your R value will also be 0 if you have one of those graphs where your dots are just nothing more than a mumbled-jumbled mess, and you can't make any sense of them. They don't fall into a linear pattern at all, and then you also will have a correlation coefficient of 0. Correlation coefficients, or your R values, always fall between 1 and -1. So the smallest it could be is -1, the biggest it can be is 1, and it can be any number in between. The closer those numbers get to either 1 or -1, the stronger the association between the two variables. So like a 0.99 is a very strong positive relationship. A negative 0.99 is a very strong negative relationship, negative linear relationship. So the positive and negative just gives you an idea of the slope, if the slope's positive or negative. And then the closer it is to 1 or -1 gives you an idea of how strong it is. If I change the units of measure, it does not change my correlation coefficient. So yesterday we looked at an example between an apple's circumference and an apple's weight. And if I measure the apple one day in inches and the next day in centimeters, it's still not going to change the relationship between an apple's circumference and weight. And so because that relationship has not changed, the correlation coefficient is going to be the same still. If I graph, for instance, the apple's weight on the x-axis and then the diameter on the y-axis versus the other way around, the diameter on the x and the weight on the y, again, the relationship between the two variables is still going to be the same, and it's not going to change my correlation coefficient or my R value. Okay? But correlation coefficients are definitely very strongly affected by outliers. So if you've got an outlier, it's going to throw that correlation coefficient off for sure. Okay, so here's some definite R values and correlation coefficients, and what we want to do is we want to be able to match the different correlation coefficients to a graph that goes along with them. So we're going to kind of start with the most obvious ones, and we'll work our way from there. A correlation coefficient right here of -0.99 means that it has negative slope, and it's a very, very strong relationship, meaning the dots are very close to falling into a perfect line. Okay, so this one over here in this upper right hand corner is the -0.99. Negative slope, dots are pretty close to a perfect line, so I use that one. This 0.9 again is another pretty strong relationship. This time it's in the positive direction, so I'm going to look for dots that are have a positive linear type of look to them and very clustered together, since it's a pretty strong relationship because it's close to 1. And so this one over here would be that. Okay. The next strongest relationship is this -0.07 up here. And that means that it has negative slope. So definitely you're looking for a graph whose line is a negative. It's got to be somewhat linear and negative. And that would be this one down here. And then you have this 0.5, so now I'm looking for one that has positive linear slope, but not a real strong relationship, but that would be up here. So that's this one. And then I've got two left, one with negative 0.3, so a negative slope, but not much of a relationship at all, and one where there's, you can't even tell if it's linear or not. And I would put this one at the negative 0.03, and this one at the 0. So this one right here has no linear relationship whatsoever. Okay? Very hard to even pick that as linear out of there. All right, then we're going to look at calculating correlation coefficients on our calculator. The data is, or the directions for that are here. They are also on your notes, so you should be able to peek at those. But know that it is there. And so we are going to kind of get some data into our calculator, and then we will calculate the correlation coefficient. So here we go. Here's some data that I want you to put into your calculator. We're going to put the fat, or what's going to go on our x-axis, into list 1, and the calories, which will go on our y-axis, into list 2. So I want you to pull up your calculator, and we're going to get the data in first. Alright, so I'm going to clear out the screen so that it's not there. Remember to get data in, you're going to hit Stat and into Edit. If you have data in there that you want to clear out, you're going to up arrow until the name of the list is highlighted, hit Clear and Enter. But I want you to put fat in list 1 and calories in list 2, and you can hit pause and do that. Okay, and then we are going to calculate the correlation coefficient. The very first time you do this, you are going to need to turn your diagnostics on, and your diagnostics are under your catalog button. And once you do this, you should not need to do it again, but the first time you do it, you're going to need to do that. So you're going to go second, 0, or catalog. Then I want you to go down to the D's, and I want you to look for diagnostics on. My calculator got a little happy there. All right, diagnostics on. I want you to hit enter to select it, and then hit enter one more time until it says done. Okay, so now my diagnostics are turned on, which is a good thing. And now we're going to calculate the correlation coefficient. Okay, so to do that, we are going to use the linear regression button. So we are going to use stat, and then over to calculate, and number 4, which is linear regression. We need to tell our calculator that our data is in list 1, comma, list 2, enter. Okay, and that is going to give us a correlation coefficient. I also want to be able to graph that data just so that you can see if it's even feasible to use to talk about the correlation coefficient right here. Because remember, correlation coefficients are not useful unless you have a linear relationship. Okay, so to graph it, I'm going to make a scatter plot. And remember, anytime you want to graph statistical data, you're going to go to second y equals. First of all, I want you guys just to go up to y equals and make sure nothing is in here first. Clear that out if you have anything in there. Okay, and then we're going to make a stat plot. So we're going to go second y equals. Again, I only want you to be looking at one plot at a time. So if number 1 is turned on, that's fabulous. But make sure 2 and 3 are turned off, or you're probably going to get an error. So go into number 1. Make sure it's turned on. You want scatter plot, or that upper left graph, picked because you're going to plot a bunch of points. Then where it says X list, you need to tell your calculator where you put, in this case, the fat grams. I put mine in list 1, so my X list should say list 1. And my Y list, in this case, is the calories, and so I put that into list 2, and so it should say list 2. And then I want you to hit zoom, and 9. Okay? And again, you're only going to calculate correlation coefficients if the data is linear. And in this case, definitely the data is linear, and so that is a good thing. It would make sense to calculate the correlation coefficient. Okay? It should look something like this after it's been graphed. All right, does calculating the correlation coefficient seem appropriate according to this graph? Yes. It follows a linear model, and that's key. And the other thing you probably should look at is if it has any outliers in there. Because if it has outliers, you probably want to take those off your list before you calculate the correlation coefficient. In this case, it doesn't. But yes, it's appropriate. It follows a linear model. I want you to notice here too that it does follow a linear model and it definitely has positive slope. So we would expect our correlation coefficient to be a positive number. And the relationship looks to be pretty strong. So it should be pretty close to 1, pretty close to positive 1. Okay? Then use your calculator to find your correlation coefficient. We already did that, but I will do it again for you just so you can see. You're going to go back to the main screen. I'm going to just clear this out just so that it's cleared again. And one more time, you're going to go Stat, over to Calculate, number 4 for linear regression. My data was in list 1, comma list 2, and hit Enter. And the correlation coefficient is the R value there, the 0.9606. And what that number tells me is that it's a strong linear relationship. And I want you to put these words in there. Strong, and actually I should put one more word in there. Strong positive, I need to throw that word in there. Give me direction so that I know you can talk about that. Strong positive linear relationship between fat grams and calories. So I always want you to put this in context for me and tell me what variables you're talking about. In this case, I'm talking about fat grams and calories and looking at their relationship. So always complete that sentence and put it in context for me, please. Okay, then here's the question. What if we had measured the amount of fat in milligrams instead of grams? What would that do to the correlation coefficient? And we talked about this at the beginning, how it doesn't matter what units of measure you use. You can change those units of measure, and it's not going to change the correlation coefficient. So it would do nothing, because changing units of measure doesn't change the R. Okay, so hopefully that's helpful for you in terms of correlation coefficients. Okay, now we're going to kind of switch topics a little bit and talk about correlation versus causation. Okay, correlation, just you're looking at different associations. Okay, there may be a cause and effect relationship, there may not. Causation, then you're looking more in terms of cause and effect kinds of things. So here's kind of a little situation that I want you to think about. If you measure the square footage of homes and the life expectancy in different nations in the world. So you measure the size of their homes and then you look at how long people live in those different countries. There's definitely a high positive correlation. Typically, nations that have bigger homes have higher life expectancies. That kind of makes sense. Okay? But here's my question. Does having a bigger home cause you to live longer? That's what you want to think about. Because if it does, then we should maybe just go to Botswana or some underprivileged countries and just build them some really big homes. Because if we build them some really big homes, maybe they'll live longer. And we know that that is totally unrealistic. So in this case, certainly the square footage of homes and their life expectancy are related to each other, but they are not, one does not cause the other. And that's the difference here that we need to think about, is what is actually the cause of the change in life expectancy, and it's not homes in this case. Okay? We can't build people bigger homes. The reason that probably they live longer is because if you have more money to build a bigger home, you also have more money to go to the doctor, to take care of yourself, to buy yourself some good food. You're probably able to drink clean water, some of those other kinds of things. Okay, you probably have time to exercise a little bit, all that good stuff. Okay? So, important to know that strong correlation does not mean that a change in one variable causes a change in another. So correlation coefficients that we talked about just measure a relationship. It does not have to be a cause and effect relationship. It may be a cause and effect relationship, but it doesn't have to be. Okay? If we really want to determine if there is a cause and effect relationship, technically we have to do experiments to do that, and we will talk more about that in another chapter. All right, so we are going to look at some different types of cause and effect relationships, ones where there is causation, and the easiest and simplest one, which is very hard and very rare to find, but there's this one type called direct causation. And all that means is if I change the explanatory variable or the x variable, it is going to result in a change in the y variable. And there is nothing else out there that really affects the response variable, or the effect in this case. So here's a very simple one. The more time I spend on a long distance call, the more it's going to cost me, period. Okay, there is, no, and you can't read too much into these. You can't go, but I could go find a different carrier and it would be cheaper and da 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 da. Okay, that's, don't make it that hard. Just very simply, a time spent on a long distance call is going to cost you more money if you spend more time, period. Okay? Then there's one called common response, where if you look at the explanatory variable and the response variable, they are not, one does not cause a change in the other. However, there's this third party out there that probably affects both of them. Okay, so it's indirect kind of causation, and it's called common response. So if I look at people who regularly worship, and then I look at people's life expectancy, I bet you can figure out that typically people that worship longer worship more regularly, I should say. Typically in different countries all around the world, if you worship regularly, their people tend to have a longer life expectancy. Now, that doesn't mean that I can just send a bunch of people to church 1,200 times a day and expect them to live to be, 809 years old, okay? So how regularly you worship does not necessarily cause you to live longer, but there's some other things that do, okay? And so it might be things like this. If you worship regularly, that means you probably do things like you take care of yourself. You let go of your stresses. You let go of stresses. Typically, if you worship regularly, you do that with other people, and so you probably have some relationships that keep you energized and fed and feeling good and all that stuff, and that increases your life expectancy. You laugh with other people, you talk with other people, all that good stuff. When you worship regularly, all of those things affect your life expectancy. Okay, so that's just an example of that one. And then there is what is called confounding, which means that there's these the one definitely causes a change in the other, but there's also a third party that affects it. Okay, so if I look at this, the body mass index of parents definitely causes a body mass index in children. Okay, that's hereditary. Okay, body mass indexes, some of it is hereditary. There's a piece of it that's hereditary. So there's definitely a cause and effect relationship there. However, it's not the only thing that affects the body mass index in children. Also, clearly, and you could list 1,012 things here too, but clearly some obvious ones, things like diet, exercise, those kinds of things, also will affect the body mass index in children. But certainly, having parents that are a certain way and certain body types is definitely a pre-indicator, a predictor of what your children's body mass index could be like. Okay? All right. So that should do it for this lesson, and I think we're good.